Okay, today we're going to be looking at the simple gas laws. They're known as Boyle's law, Charles' law, and Gay-Lussac's law. And they're actually derived from what we know as the combined gas law. Now, before starting, there's a few things we need to talk about. Gases behave in different ways, and they obey mathematical laws. But when we're discussing gases, we're assuming that we're always dealing with what we call an ideal gas. And an ideal gas basically just obeys all of the laws at all conditions of temperatures and pressures. Now keep in mind, as always, there are some exceptions, but today we're going to be focusing in on those normal ideal gases that obey all of the mathematical laws. There are some temperature and pressures in which they tend to deviate a little bit from the laws, and that's not important for us right now. We're just dealing with the basics. So I want to go ahead and look at this combined gas law. Basically, all three of the simple laws are combined into one expression, and that is looks like this. You have a pressure 1, so that's the beginning or initial pressure, and a volume 1 multiplied together divided by temperature 1. So all of these are the initial conditions of a gas. And then we look at how these variables respond at different pressures, different volumes, and different temperatures. So this has all three of the simple gas laws combined into one expression. So I wanted to look at kind of the big picture, and then we're going to look at the pieces of the puzzle. So the first one we're going to focus on is known as Boyle's law. And it says for a given mass at a constant temperature, the volume varies inversely with pressure. So this is, again, mathematical terms, inverse and direct proportions. This is what the gas law would look like. It would only have the pressure and the volume variables because the temperature is held constant. So, thinking about what an inverse proportion means, if volume goes down, then pressure does the opposite. If volume increases, so if your container gets bigger, then the pressure of the gas is going to decrease. Now, if we go back and we look at that combined gas law, if we take out temperature, then that leaves us with pressure and volume, and that's what's known as Boyle's law. Now, if you look at this illustration here, notice you have a container with a given amount of gas particles in there. Remember, the collisions of gas particles is what generates the pressure. Notice here that the temperature is 298 Kelvin in each picture here. And this is really what we call a movable piston. So it's able to compress or expand. Notice the pressure is 1 atmosphere, the volume is 1 liter. Notice here the pressure is doubled and then the volume is 0.5. Now think about an inverse. If you take the inverse of a number, you put 1 over that number. So double the pressure. 1 over 2 is 1/2. You should have 1/2 of the volume. Now look at the pressure is 4 atmospheres. So that is quadruple that beginning pressure. So the volume should be 1/4 of the initial volume, and 1/4 of 1 would be 0.25 liters. Now if we graph that data, we get a curved line when we're looking at Boyle's law. Inverse proportions give you a curved down line that looks like this. So let's look at an example with Boyle's law. It says a balloon is filled with 30 liters of helium gas at 100 kilopascals. Notice there, this is a volume. Your unit tells you what you have. Liters is volume. And then this is your pressure. That's the beginning stuff. So this is V1. And then you have your P1. What is the volume when the balloon rises to an altitude where the pressure is 25 kilopascals? So you're trying to find the new volume, which would be V2, at a new pressure, which is much lower. As we go up in the atmosphere, the air gets thinner, and that causes the pressure to be less because you have less particles and there's less collisions. So we know that temperature is not mentioned here. If it's not mentioned, we know that means it's held constant. And basically, we're left with just the Boyle's law part of the combined gas law, P1V1 equals P2V2. So there's your 100 kilopascals, that's your pressure 1. Then you have the volume 1, 30 liters. And then you have your pressure 2, 25 kilopascals, and you're solving for V2. So mathematically, we're going to have to simplify 100 times 30 and then divide that by 25. And so then that's what you would be typing in your calculator. And when you do that, you should get 120 liters. And then think about it. Does that make sense? Pressure and volume are inversely proportional. Your pressure went down, so your volume should do the opposite. So as a balloon rises in the atmosphere, it's actually going to expand because of the gas law. Now let's look at one more example with Boyle's law. It says the pressure of 2.5 liters of an anesthetic gas, so that's usually something to put you to sleep, is changed from 100 to 40 kilopascals. What will be the new volume if the temperature remains constant? Now this one does mention temperature. It says it's constant, so constant means don't worry about it. It's not a factor in this problem. If it doesn't mention a variable, then we assume it's held constant there. So again, we have a volume here, and we have a pressure. The pressure is going down, so we would expect, because this is inverse proportion, we would expect as the pressure goes down, the volume to go up. So then we substitute our values. We have the 100 kilopascals for pressure 1. Volume 1 is 2.5 liters. What will be the new volume? So again, we're solving for V2, and we have that new pressure of 40 kilopascals. So then, of course, we will be multiplying 100 times 2.5 and divide that by 40. So take just a minute, practice putting that in your calculator. So pause your video. And you should get an answer of 6.25 liters. And again, that makes sense. The pressure decreased, the volume increased. Now we're going to look at another version or another part of the combined gas law, which is Charles's law. And basically it states that the volume of a fixed mass of gas is directly proportional to the temperature in Kelvin if the pressure is kept constant. So this is basically now we're not worried about pressure. We're looking at volume and temperature here. Now, when we're dealing with any of the gas laws, the temperature must be in kelvins. So to get the kelvins, we add 273, that's a constant value, to our degrees Celsius, and that will convert to kelvins there. Now, these are directly proportional. They're divided. When you divide to get a constant value, you get a direct proportion. So now we're getting a straight line, unlike Boyle's law, which had the curved line. We get a straight line with a constant slope. Now again, there's your reminder there. So if we had 0 degrees Celsius, we would need to convert that to Kelvin. That would be equal to 273 Kelvin. So looking back at the combined gas law, I want you to see how all of the simple gas laws are a part of the combined gas law. So now we're holding pressure constant. So that drops out of the equation. and we just have volume over temperature and volume over temperature. And this is an example or illustration of Charles's law. It says, as a balloon is cooled from room temperature with liquid nitrogen, its volume decreases. So notice how that liquid nitrogen is poured onto the balloon. It's going to rapidly decrease the pressure, and it causes that balloon to shrivel up. You could also do something similar to this at home. You could take a balloon and you could take a piece of string and measure the circumference of the balloon. Put it in your refrigerator for a couple of hours and take it out, and you're going to see that the balloon has gotten smaller. It's decreased in its size, which would be the volume of the balloon. Now let's look at an example with Charles's law. It says a balloon inflated in a room at 20 degrees Celsius, so there's your temperature 1, has a volume of 10 liters. That's your volume 1. The room is heated to 40 degrees Celsius, temperature 2. What is the new volume of the balloon? So we're solving for V2 if the pressure is unchanged. So now they're telling us pressure is unchanged. Again, if they didn't mention pressure, we would know it would drop out of that equation. So now we're looking at volume 1 over temperature 1 equals volume 2 over temperature 2. Go ahead and convert to Kelvin. So 20 plus 273, temperature 1 would be 293 Kelvin. Temperature 2, 40 plus 273 would be 313 Kelvin. So then, of course, you're going to set up your proportion. Your volume 1, 10 liters over temperature 1, 293 Kelvin. Volume 2 over temperature 2. Now, most of the time, I know you like to cross multiply. So, however you like to solve, you can cross multiply and then divide. Really, you can multiply and divide in any order, but you can say 10 times 313 divided by 293, and you should get 10.7 liters. Now, these are rounded, these answers, to the nearest 10th place. Normally, we use the 100th place, so tenths or 100th places, it really doesn't matter as far as I'm concerned with the rounding there. So at least keep 1 decimal place for your calculations there. So again, this makes sense. Volume should increase when the temperature increases. So now we're looking at direct proportion. So your temperature went up, your volume should go up. So your answer makes sense. Now we're going to stop today with Boyle's law and Charles's law. Tomorrow we'll look at the next part version of the combined gas law. We'll look at Gay-Lussac's law, and then look at an example of how to solve problems when nothing is held constant. So when you use that original form of the combined gas law.